Shall we start?
Yeah, it's fine by me. Yeah, sure.
So, okay. So a warm welcome to those of you who are here in this room, and also it's in the hybrid mode, and a lot of people are joining online. And welcome to all of you. This is the inaugural colloquium of the Department of Mathematics at IIT Bombay this semester, and it is also part of the distinguished lecture series of the Indian Mathematics Consortium, which has been happening now for roughly 2 years, October 2020 onwards. And this colloquium is also part of the distinguished lecture series of the Indian Mathematics Consortium. And this is jointly hosted by IIT Bombay as well as ICTS TIFR Bangalore. So we have great pleasure in introducing today's speaker, Professor Dipendra Prasad. And I don't need to say many words about Dipendra Prasad. And we are happy to have him as part of this department for last several years. And he will give this inaugural colloquium of this semester of the department. And we are back to some kind of normalcy. So this is hybrid, and there are a lot of people in this auditorium. And Dipendra will speak on the tensor product of representations of classical groups.
All right. Thank you, Anand. You know, I must say that I am one of the organizers of this colloquium series, myself and Jugal Verma. So it looks a bit strange that I have invited myself to give the first talk. Actually, what happened was that I organized the next colloquium after 2 weeks, and there was some space available. Then I said maybe I could lecture. In fact, the thought came at a time when one of my students, Dibyendu Biswas, was completing his first paper. And indeed, I was very happy that he was completing his first paper, and I was quite excited. And he submitted the paper like middle of July, and that is about the time when I proposed to give this colloquium on his work. Although we were very pleased to have submitted, that happiness was not for too long, because a few days later, we learned that whatever has been done in the work was already done a few decades ago, although the methods of the proof are different. So still the work has some worthiness. In any case, this is not a technical lecture. I am not going to give you any proofs, but the purpose of my talk today is to generally give a little bit of introduction to representation theory of groups. So I will not be too specific at most of the places, but I will begin in some more precise way. Although Dibyendu's work is for most part about classical groups, somehow the work was first conceived for GLN, which is the first classical group and which is the most familiar of all groups. And perhaps for the lecture today, I will restrict myself only to GLNC, being the most well-known among groups. Okay, so the group of interest. The group of interest is GLNC. So these are n by n complex matrices with determinant which is non-zero. It can be defined over any field, but I think complex numbers is okay for me. And for the purposes of group theory, what is important is that this group has this group of upper triangular matrices which contains this group of diagonal matrices. So this B is often called B upper triangular matrices, and T is the diagonal matrices. So the diagonal matrices can be given a coordinate form, and there are many options to choose the coordinate system T1, T2, Tn, or x1, x2, xn, or z1, zn, z2, zn. I seem to have chosen T1, T2, Tn for the coordinate system for the diagonal matrices. And then there is another group, the normalizer of T, which is the group of monomial matrices. And NT by T. So NT is the normalizer of the torus inside the group G, and NT by T is what is usually called the Weyl group, and which for GLN is equal to the symmetric group on n symbols. It just operates as permutation matrices on the torus. Okay, so this is all that we need from group theory. And then we need a few things from representation theory. So representations. So all the representations are finite dimensional. All representations are finite dimensional. And by a representation, we mean a mapping from your any group G to automorphisms of a vector space V, where V is a finite dimensional vector space over C. So this is what a representation is, and one of the basic problems, or rather two basic problems in representation theory. So basic questions. Is one, classify irreducible representations. Try to decompose naturally occurring representations in irreducible in terms of irreducible representations. Of irreducible.
क्यों ला के रख लो बे, काम तो आ ही सकती है, उसमें क्या खराब तो नहीं ले आकर रख लो ना, मतलब इनके फिर से चढ़ेगा कुछ होगा।
Okay,
दिक्कत
so
नहीं, रखनी चाहिए वैसे बे।
I think question one, of course, is a very precise question. Classify irreducible representations. The second question, try to decompose naturally occurring representations in terms of irreducible representation, perhaps is not as precise a question because one doesn't know what is a naturally occurring representation. But we will have some occasion to see some instances of that. So as I said in this lecture, the group G is GLNC, and we are looking at its irreducible representations. So I think first courses in representation theory tell us that representations are classified by their characters. by their characters, which means that i.e. so if I denote capital theta of rho at the element G to be trace of rho G. So this element, which is a complex number, as G runs over the group, it determines the representation uniquely up to isomorphism. And that is also the case for GL and C. We also know that this character is a class function. It depends only on the conjugacy class. And we know that almost all conjugacy classes can be diagonalized. Almost all elements in the group GL and C can be diagonalized. So the character theory amounts to understanding the character restricted to the torus. So thus representations of GL and C, representations of GL and C are functions on the torus, functions on T. But on the torus, the normalizer of the torus still operates. So these are functions of T1, T2, Tn, which are invariant under the Weyl group. So they are functions on T, which are invariant under W. Under the symmetric group Sn. So so character of a representation is a function on the torus. Torus has the coordinate T1, T2, Tn, and these are invariant under the symmetric group. And it is a fact that the representations of GL and C of interest are somehow algebraic representation, and therefore the character on the torus is a polynomial in T1, T2, Tn. So for representations of interest, this theta rho T is nothing but a symmetric polynomial. Nothing but a symmetric polynomial. Symmetric polynomial, i.e. an element of Z T1 Tn Sn. So this ring you have all seen, ring of symmetric polynomials with integer coefficients. So these are with integer coefficients, and so each irreducible representation or each representation gives rise to a symmetric function. And somehow the question is to understand which symmetric functions arise as characters of irreducible representations, and to understand their nature in some ways. And then maybe the second question is to decompose certain naturally occurring representations. So part of the representation theory of GLN or of classical group, or in general any group, is an exercise in invariant theory. We are trying to understand symmetric polynomials. So yeah. So of course, symmetric polynomials are of course well known to all mathematicians. It's perhaps a very large subject, but I do want to say a few words because somehow it is relevant to what I am talking about today, that the algebra of symmetric polynomials Zt1, Tn, Sn itself is a polynomial algebra on elementary symmetric functions. So it is known that Zt1, Tn, Sn is a polynomial algebra with generators, and there are many kinds of generators. I think the generators that one somehow first learns about are the elementary symmetric functions EI, which is so maybe I wrote them as EK. So EK, so these are written as summation of TI1, TI2, TIK, where I1 is less than I2 is less than IK. And you sum it over all from 1 to n. So these are all from 1 to n. So these are called elementary symmetric functions. Then there are things called full symmetric functions, I believe is the name, HK, which is the same sum, TI1, TIK, but instead of less, it is less than or equal to I1 less than equal to I2 less than or equal to IK. And then there is another one which is also quite useful, PK, which is T1 to the power K plus Tn to the power K. So I think many of you know about these bases, and these two are basis over Z, and this one is a basis over Q. When I say this is a polynomial algebra with generators that, I guess it means that this HK or PK is less than or equal to n. I mean, for EK, of course, beyond n, it is 0. I mean, but these things are there beyond n also, but we count only up to n, and this one also up to n. The first two are basis over Z. The third one is a basis over Q. But these are basis of the generators of the algebra, which means that any element is uniquely a product of a linear combination of them. It's a linear combination of a product of them. Okay. So of course, the elementary symmetric functions are obtained from this identity x minus TI product. This is same as there is plus minus, so maybe I don't want to deal with plus minus, so let's say x plus TI. X plus TI is equal to x to the power n plus E1 x to the power n minus 1 plus dot 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 plus En. Then there is this identity product of 1 minus Tix. Yeah, so maybe I should have done that also differently. This is equal to, so the word I used was HK. So this is 1 plus H1x plus H2x square plus dot dot dot. And because roughly the second is the inverse of the first, it also proves that if the first one is a basis, then the second one is also a basis. Good. So there is another basis of symmetric polynomials. Which we will call, which are called Schur polynomials. Schur polynomials, and they are defined by an n tuple of integers. Lambda bar is equal to lambda 1 greater than equal to lambda 2 greater than equal to lambda n greater than equal to 0, and these are n tuple of integers, and which are actually the characters of certain irreducible representations pi lambda of GL and C. So yeah, so in some sense, the main theorem of the subject, in some ways, the only theorem in this subject is the following theorem called Weyl character formula. Weyl character formula, which says that so the Weyl character formula is a formula for all connected algebraic groups, but I say it only for GLN. But in some sense, there is not much difference between GLN and other groups. So other groups may need a little more notation, but except for some notation, it's the same theorem. So theorem says that irreducible representations of GL and C are in bijective correspondence with lambda bar equals lambda 1 greater than equal to lambda 2 greater than equal to lambda n elements of z to the power n. They are in bijective correspondence, and their character is given by so as I said, to understand the character, it suffices to understand it on the torus element T1, T2, Tn, and it is given by a certain ratio of two determinants. These two determinants are somehow called Vandermonde determinants, and The one defined is t to the power lambda n, t1 to the power lambda n minus 1 plus 1, and dot 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 t1 to the power lambda 1 plus n minus 1. So what you do is you have lambda 1 greater than equal to lambda 2 greater than equal to lambda n. You add to this lambda something called half sum of positive roots, which is n minus 1, n minus 2 dot 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 0, 0, 1 dot dot dot. You add it up, and then you write this lambda n minus 1 plus 1, and it goes up to lambda 1 plus n minus 1. So this is you do for t1, and then you just permute t1, t2, tn. Tn to the power lambda n, tn to the power lambda n minus 1 plus 1 dot 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 tn to the power lambda 1 plus n minus 1. So once you know the first column, the other columns are the same, replacing t1 by t2, t3, tn, and it is this. And in the denominator, it is the same thing, but for lambda i's to be 0. So you start with 1, 1, 1, 1, 1, and then t1, t2, tn, and then t1 square, t2, tn square, and so on, t1 to the power n minus 1, tn to the power n minus 1. So this is the ratio of these two determinants. Each of the determinants is a skew symmetric polynomial. And you know, one of those arguments that one studied early on, that the determinant on the denominator is product of ti minus tj. So this determinant, of course, we know is ti minus tj, I less than j. And the proof that we all learn in, I don't know when, that it is a skew symmetric polynomial, and therefore it is divisible by ti minus tj for all I less than j. Because by definition it is skew symmetric, and therefore it is divisible by ti minus tj. And then on the two sides you compare the degrees. So then the degrees are the same, and therefore up to a constant they are the same. And then you make a small observation about the leading term of t1 to the power n minus 1 and something or the other. So that determinant, one of those beautiful arguments, proves it is product of ti minus tj. But that same argument also works to prove that the denominator divides the numerator, because the numerator is also a skew symmetric polynomial, and therefore it is divisible by ti minus tj, and therefore by the product. And okay, so you get the quotient of two skew symmetric polynomial is a symmetric polynomial now. So you have gotten hold of a symmetric polynomial, and so this I have not tried finding out whether this was known long before Hermann Weyl, or he also came up with this formula. But in any case, one of the great achievements of Hermann Weyl, certainly from what mathematics I pursue, is this Weyl character formula. It is for all groups, but in some sense, as I said, other groups are just some minor notational changes to GLN. And in some sense, this is the only theorem in the whole subject, Weyl character formula. Each and every irreducible representation is parameterized by these have a name, dominant integral weight. lambda 1 greater than equal to lambda 2 greater than equal to lambda n. This is called dominant integral weight. So each irreducible representation corresponds to a dominant integral weight, and then its character is there. So there is nothing more to be done. So of course, you are looking at all representations, but there is also this other theorem which was also proved by Schur-Weyl, that every representation is a direct sum. The category is completely reducible, just like for finite groups. Every representation is a direct sum of irreducible. Schur-Weyl also had the very famous Unitarian trick, which proved that every representation of GLNC or GC, etc., is direct sum of irreducible modules. And for irreducible module, the character theory is the ultimate. Everything is should be eventually should follow from the character theory. So it is surprising, one would say, that once this theorem has been proven, there is anything else that could still be worthy of pursuit. Okay, so all right, this is one point of view. The character is there in front of you, it's simple-minded and all that. One of the difficulties in the subject is that typically this character formula is a quotient of two polynomials. And one of the great difficulties of the subject is that it's very difficult to divide polynomials. So I think that is one problem as I see. So it's very difficult to divide polynomials. In particular, the fact that this polynomial has some value at t equals 1 also needs some cleverness. If you are given a polynomial in t1, t2, tn, you can put ti to be 1, which gives the character value at identity element, which is the dimension of the representation. But in this case, it is going to be 0 upon 0, because you have a skew-symmetric polynomial. A skew-symmetric polynomial at identity matrix takes the value 0. So it is 0 upon 0. But of course, we know calculus teaches us how to deal with 0 upon 0. And even though I know how to deal with 0 upon 0, I don't think I could have come up with what Schur-Weyl did. So there is a way to calculate theta lambda of 1. So this is called Weyl character formula. As I said, one of the difficulties with the Weyl character formula is that it is not a simple formula, but it is a quotient of two polynomials. And dividing polynomials is a bit of a difficult task. So much so that even to evaluate it at identity, it needs effort. And therefore, it is worthy to call this a theorem. So this is indeed called a theorem. And this is called Weyl dimension formula. Dimension formula. And what it does is it calculates the dimension of V lambda, which is nothing but theta lambda at 1. As I said, calculus teaches us how to calculate 0 upon 0, and it's legitimate and so on. But so in any case, the answer of that calculation is that this product is lambda I plus I minus 1. Lambda I plus I minus 1 minus lambda j plus j minus 1, this one product over I less than j upon product of with lambda I to be 0, which is I minus j, I less than j. So this is the answer, and it's often remarked that one doesn't know how to prove that this is an integer, but I guess it's dimension of a representation, so it is an integer. So this is a Weyl dimension formula, and it tells you the dimensions of all irreducible representations, and Weyl character formula gives you all the characters. Okay, so this is one way of dealing with representation theory, abstract, complete generality. This is the path which is pursued by Harishchandra for all reductive groups, and we are all justly very proud of that. But you know, given the explicit nature of groups, maybe we can try to do something simple-minded and see where it leads us. So there are more pedestrian ways of going about representation theory, and I do want to say a few words about that. I want to say a few words about what is the most obvious way of dealing with representations. So, you know, we are as I said in this lecture, we are looking at representations of GL and C, and so GL and C, of course, comes with a representation, the tautological representation into GL and C. And we can try to construct some representations randomly. So we begin with this standard representation V, and then we can do V tensored V. And we all know that V tensored V is not an optimal thing. We can reduce it. So we can write it as sim square V plus exterior to V. And with luck, maybe this is the only decomposition which happens, and this is the case. But already, if you want to do V tensored V, tensor V, then this method, I think, okay, not too difficult, but it starts to give you a little hard time. So V tensored V, we know from the previous line, is sim square V plus exterior to V times V. So we write it as sim square V tensor V plus exterior to V tensor V. Now what? So this is not the complete decomposition, and we hope to find some more components via this process of symmetrization and so on. And it is true. So, you know, there are two things one can do. Sim square V tensor V, we can go to sim cube V. And from exterior to V, tensor V, we can go to exterior 3V. So here, like V1 wedge, V2, tensor V3 goes to V1 wedge, V2 wedge, V3. And here, V1 tensor V2 tensor V3 goes to V1 tensor V2 tensor V3. But okay, so these are natural mappings, and therefore kernels and co-kernels are modules for GLV, and yeah, so in the first case, I think sim cube V perhaps is the bigger of the two, and in the second case, it is exterior 2V tensor V, which is the bigger of the two, and we can calculate co-kernel of the first and kernel of the second. So if you do the co-kernel of the mapping 1, and this is the mapping 2. So dimension of co-kernel of 1. So what is the dimension of the image? So we know sim cube V, we know all very well, D into D plus 1 into D plus 2 by 6 minus D into D plus 1 by 2 into D. So no, I was wrong. That object is a bit smaller, so I will do this. And I did that. But maybe the relevant thing is not so much that, but we just leave it like that. And dimension of the dimension of co-kernel here also, co-kernel of 2 is D into D minus 1 into D minus 2 by 6 minus D into D minus 1 by 2 into D. So there are two observations to be made here, that in fact these two dimensions are the same. Dimensions are same. So in fact the representations are going to be the same. But there is a certain symmetry which is quite evident here, that if you change D into minus D, you go from the first set of data to the second set of data. D into D plus 1 into D plus 2, if you change D to minus D, is equivalent to changing all the signs to negative signs, and it goes to D into D minus 1 into D minus 2, and D into D plus 1 into D, when you change D to minus D, will go into D minus 1. So there is a certain symmetry between symmetric algebras and tensor algebras, a certain duality which is quite curious, especially because one of the algebras is finite dimensional and the other algebra is infinite dimensional. So the upshot is that this V tensor V is equal to, so this symmetric square V tensor V decomposes as sim cube V, plus there is a certain other representation which arises as common kernel of the two maps, and we may call it sim 2, 1 of V, and then there are two copies of that plus exterior 3. So this is the decomposition that one achieves for V tensor V. And we can repeat the process. So we are constructing from the simplest object V to V tensor V to V tensor V, and then higher tensors, and we are hoping that we can decompose, and maybe we can get a hold of all the irreducible components this way. So indeed this process also works. This is what is called Schur-Weyl duality, in which the representation theory of GLV and of the symmetric group comes together. And I am partly speaking about it because in the final theorems that Dibyendu proves, we don't do manipulations with the Weyl character formula, but we do manipulations of this kind. So we construct representations by some inductive process, and saying that more complicated representations can be obtained by some simple process. So we will come to that. Okay, so maybe I take a pause. If there is any queries, I am happy to respond to them. All right. Okay, so maybe I should now say a few words that this work is about tensor product of irreducible representations of classical groups. So some observations. So the question that one is trying to understand is that if you are given two irreducible representation pi lambda tensor pi mu, this may not be irreducible, and you want to decompose it as sum of irreducible. Somehow that is what the question is about. Yeah. So if you want to write it out, pi lambda tensor pi mu, you will write it as pi mu, and then there will be some coefficients lambda mu and some one. So the question is which highest weights nu appear in this decomposition and what is their multiplicity. So in terms of character theory, you are given the character of pi lambda and of pi mu, you take the product and you want to expand it out in some ways. But the thing is that although everything is explicit, both from Weyl character formula or from the Schur-Weyl point of view, the questions about tensor products don't have any simple answers often. Okay, so there is a very, very famous theorem called Littlewood-Richardson rule. Littlewood-Richardson rule. So it is a combinatorial description of which representations appear and also what is their multiplicities. It is a very, very complete theorem. It's also not so difficult to explain what it is, but I did not prepare myself to do that here. I have known this word, Littlewood-Richardson rule, for many decades. I cannot say I follow it too well, but there is a simpler version of it with which I have fallen in love. It's called Pieri's rule, and it is kind of a very, very baby version of Littlewood-Richardson rule. And as I said, Littlewood-Richardson rule is a very general and a complete theorem, but a bit complicated. Pieri's rule is a very special case, but it is very simple-minded also. And for the work of Dibyendu, in some sense, that Pieri's rule was enough. And I want to say a few words about Pieri's rule, and then I want to make some other general remark. So Pieri's rule is not about pi lambda tensor pi mu, which are general irreducible representation, but just general representation you multiply by sim kv. So it is a particular tensor product and it has a very beautiful structure. But maybe just to say the beautiful structure, maybe I just want to say what is pi lambda tensor V. So V is the standard representation of GLV, and you take an irreducible representation pi lambda and you multiply. So you see this lambda, as I said, is lambda 1 greater than equal to lambda 2 greater than equal to lambda n. And often these are expressed by Young tableau. So lambda 1 then lambda 2, then lambda 3, and so on, lambda n, lambda 1, sorry, non-negative integers. Yes, yes. So one might say for some convenience, I take them to be non-negative, but non-negative. So this is the combinatorial way to express the highest weight. And the description for pi lambda tensor V is that you are supposed to add one more box wherever you feel like, keeping it a Young tableau. So, you can put it on the first one or second one or the third one or the fourth one or the fifth one. If there were two things which were equal, then you cannot put it in the second one because it will become larger. So if your Young tableau was like this, then the only way you can put it is here. There is nothing else you can do. Or below, sorry, yes, yeah, yes, or below. Good, thank you, Murli. Yes, yeah. So, and this is the recipe for pi lambda tensor V, and the recipe for pi lambda tensor sim k is that you are supposed to put k boxes, and the word is that these are k horizontal boxes, which means that suppose k is 3, then you can put 3 here, or you can put 2 here, 1 there, or you can put 1, 1, 1, 1. But what you are not supposed to do is that you put 3 in which one of them, 2 of them are in the same column. So they should be on a horizontal line, and no 2 should be on a vertical line. So the Pieri's rule for pi lambda tensor sim k says that for tensoring with sim k, you are supposed to add k boxes. Keep it a Young tableau, and the only constraint is that on no column you are supposed to add 2 of them, or more than 1. So each row you are supposed, you can put 1 or 0 or many, but on any column, so you cannot put 3 here. This is not allowed because that will be in one column, not allowed. Okay, so this is called Pieri's rule, and as I said, Pieri rule. This is quite convenient, and maybe it's also a question of being comfortable with some ideas. When you have worked on it for a few months or a few years, they all seem very obvious. But Pieri's rule is, compared to Littlewood-Richardson, quite a elementary one. I think Littlewood-Richardson is also a more complicated recipe of this kind. All right, so there is one more observation to do the general representations, and then I also want to make some more observations, and then maybe a bit of the statements of the theorems. But I think I am running out of time. So, okay. So I think the first, so Pieri to general. So Pieri's rule is about pi lambda tensor sim k. So if this pi lambda itself is some product of sim i's, then maybe you can just combine the sim i's, and Pieri itself will be enough. So that is indeed the case. So the observation is that pi lambda with the same notation that we are using is in fact contained in sim of lambda 1 v tensor sim lambda 2 v tensor sim lambda n of v, and what is left in this after pi lambda is something of a little lower order. There is some amount of mathematical induction which says that in this module pi lambda is the main term and then there is a bit of an error term. So if you understand it in this way, then similarly pi mu is contained in sim mu1 v tensor sim mu n v. Now if you want to take the tensor product, so as I said, these two tensor products is roughly same as those tensor products, but Pieri's rule allows you to understand this is a large tensor powers, but you can decompose that one by one. Sim lambda 1, sim lambda n, then sim mu1, sim mu n, and this sim mu n you can absorb in the previous one, and so on. So somehow Pieri's rule allows you to get a handle of all representations in terms of the symmetric power representations. So the strategy of some of the theorems for tensor product is that you try to prove for tensor products of the form pi lambda tensor sim kv for all lambda and all k, and then you bootstrap it to sim k1 times sim k2 and so on. All right, so I don't have my time is perhaps getting up, and obviously I have not done justice to Dibyendu's work, but I do want to say a few words both about his work and about something else. So maybe I don't want to write too much. It may appear that these questions about tensor product, etc., are some small technical details, and one can do them. That is true. I think in terms of computational power, there is a lot of power, and one can do many things. But there are many theoretical phenomena which one could hope to discover about tensor products. And it is not clear that having Littlewood-Richardson rule or these other computational recipes allow you to do that. So I just want to mention to you two such theorems. One is called the saturation problem. And this is a theorem due to Knudsen and Tau. And theorem for only for GLN, and somehow for classical groups this is not correct, and I don't think the last word is out about it, and it is a very simple problem. It says that if pi lambda is contained in pi mu tensor pi nu, if and only if pi of n lambda is contained in pi of n mu tensor pi of n nu. So this can be asked for any group, and Knudsen and so this is called saturation problem. I could not know who coined this word saturation problem, who it came from. From what I understood, it is from the Russian school of Klitschko. Klitschko is famous in many parts of group theory, and so this problem is of very classical origin. And as I said, Littlewood-Richardson certainly is telling you which representations appear, This is a very special case of that problem, and it should have a bearing on it, but it doesn't. And this is yeah. So this is one of the important landmarks in our subject, and there are sorry, all n, meaning if and only if. So if it is true for this, then it's true for all n. And if it is true for one n, it is true. So the this direction is the main one. If it is true for 3, then it is also true as it is. Multiplicities, no, perhaps multiplicities it is not true, but I don't want to say anything about that. No, multiplicity is perhaps not true. Okay, but I do want to say that there is this famous problem, Horn's conjecture or problem, which is another very simple-minded problem. Given Hermitian matrices A and B, with eigenvalues lambda and mu, so these are n tuple of real numbers. What are the eigenvalues, the possible eigenvalues of A plus B? So I think the problem, of course, is that if you are given eigenvalues, then you know the conjugacy class of A and of B, but not of A plus B. So there are many possible eigenvalues, and these two problems are about the same problems. I cannot imagine how they are the same, but as I was trying to prepare this lecture, I learned something even more elementary than the Hermitian matrices, that this problem is also equivalent to knowing for which finite abelian groups P, Q, R, there is an exact sequence, exists an exact sequence. 0 goes to P, goes to Q, goes to. So, yeah, I would not have imagined that somehow a question about finite abelian groups, which in my youth I never thought much about. I have no answers. Okay, so yeah, so so this was one problem which as I said, has been solved for GLN, but is not understood for other groups, other classical groups also. And then I want to end just one last one or two more minutes. I was working, so in some ways in last few years I have been interested in computational mathematics, and with one of my friends, Vinay Wagh, we were trying to understand what does the tensor product really look like. So you know, you have some representation pi lambda tensor pi mu, and you know, it is a certain summation of pi nu and some coefficients n nu lambda mu. So the question is, if you are given lambda and mu, how many nu's and what are the structure of the coefficients? And so we did some computational work. Okay, so perhaps there was a theoretical region and then there was some experimental work. You know, we were to give a specific example, D8, which is SO16, and I looked at the representation pi, which has highest weight 6, 5, 4, 3, 2, 1, 0, 0, and I looked at pi tensor pi. So, you know, everyone will say that, you know, it's a small representation and so on. But, you know, what I found, or rather what Vinay Wag found, that this pi tensor pi has 28,920 irreducible representations. And the maximal multiplicity is 5,198,896. And it is attained for a certain representation and is attained for 7, 6, 5, 4, 3, 2, 1, 0, 0. And in some sense, one of the purpose of my work with him was to relate multiplicity questions on classical groups and GLN. And we also wanted to find some statistical behavior of multiplicities. So, you know, here there are these two numbers, 28,920, and then there is this number 5,198. And somehow the question which interests me greatly is to come up with a model to model these two numbers. So, yeah, so I end there. Thank you. I'm sorry, you know, in some way I have not done justice to Dibyendu's thesis, but so he will lecture.
So thank you so much, Dipendra, for this lecture. And now the floor is open for questions. Both from this room,
you know,
and
there are many
from,
things which I could not talk. So if you ask, then I
yeah,
will get more time to talk.
So from this room, as well as, you know, the people who are there in the virtual world, and probably via chats also, where I guess someone will help me out.
Yeah, Sudhir, yes. Dibyendu's main theorem is, you know, right. There are two theorems, neither of which I came to. There is a way of going from GLN to GLN plus 1 by adding a 0 to the highest weight, lambda 1, lambda n, and you put a 0. You put a 0, you get GLN plus 2, and so on. By putting a 0, you have changed the representation in many ways, but also there is some feature of it which has remained unchanged. And the Dibyendu's theorem talks about whether this operation of going from, so you can take two representations on GLN and you can take their tensor product on GLN. Or you can go to GLN plus 1 by adding a 0 and you can take the tensor product there. And the question is, how does the tensor product on GLN behave with the tensor product with G? What is the relationship of the tensor products? And the theorem is that after few steps, the tensor product stabilizes. So it may change. So you may take the tensor product on GLN, you will get a certain result. The result will be different on GLN plus 1, but there is a specified integer d, beyond which on GLN plus d onwards, the tensor product would be the same. So it's a certain stability phenomenon about tensor products. Coefficients are the same. Meaning, you know, as I said, there is a way to embed representation theory of GLN in GLN plus 1 by, for every representation, you put a 0. So you can do for pi lambda, for pi mu, and for each representation in the tensor product. And the fact is that this operation of taking tensor product in GLN or GLN plus 1 or the later ones, after a few steps, stabilizes. And of course, the main point is that how many steps are needed for it to stabilize. And the theorem is that if the highest weight lambda consisted of k rows for pi lambda and L rows for pi mu, then you will need to go to at least k plus L, beyond which it will become stable. And there is a similar theorem for classical groups. And then his other theorem is that among classical groups, the representations are classified by n tuple of positive integers once again. And somehow which classical group you deal with, somehow it doesn't matter for this stable multiplicities. And these are all consequences of Pieri's rule, because as I said, if you have a tensor product with a sim k, Pieri's rule says everything that you would like to understand. And then it is bootstrapping the Pieri's rule from sim k to the tensor product of the sim k's. Yeah, so that's a summary of what he has done.
There's a version of Pieri's rule for classical groups.
There is a version of Pieri's rule for classical groups, indeed. Perhaps not as well known as Pieri's rule for GLN, but there is one. Yeah. Sorry?
Fulton-Harris Pieri's rule will be only GLN.
Not because it could not have. I do not know why. In some sense, you know, to tell you the truth, the Pieri's rule may belong to several hundred years ago. And even for classical groups, it must be 100 years old. But the only reference which Dibyendu has been able to find, and I have been able to find, is in last 1 decade or so. But sorry?
No, I remember now. Dibyendu CPS, he quoted something more.
Yeah, Okuda. But that is a recent one, but I cannot imagine that it was not known 100 years ago. Murli, you want to say something?
Pieri's rule is in symmetric function literature. The same rule.
No, but no, for classical groups. Classical groups.
Yeah, but there it's well known for a long time. Instead of saying in the representation, you will say how to multiply a Schur function with a complex.
Yeah.
And how to expand.
Yes, yes.
That's precisely
No, no, it's the same thing. But I think the question is, I feel embarrassed to refer to a literature which is only 5 or 10 years old when it should be hundreds of years old.
Yeah, this rule is well known.
No, for classical group. No, for GLN, I know we. Yeah.
I don't know. But it should be known, but I don't know.
Yeah, perhaps not.
Sorry, I'm not very good with the new technology. How do I know whether there are questions from? Yeah. You need the mic? Yeah.
Hi. People can unmute. You can
So if there is anyone who would like to ask a question, and we welcome you to ask questions, please unmute and ask.
Hi, Anand. Can I ask?
Go ahead. Yeah.
Yeah. So, Dipendra, you mentioned about that there is an inductive construction in Dibyendu's work, and you were responding to Sudhir's answer. That in that you mentioned the inductive argument, is it the same inductive argument that you were talking about?
Yeah, I mean the inductive argument, I perhaps cannot give a very pointed response. In the text, I wrote down a certain tensor product of sim lambda 1 tensor sim lambda k, and I said it contains this pi lambda, and the other representations which appear have highest weight somehow less than lambda. So I think we do some induction on how big is lambda, and assuming that the theorems to be proven are known for lambda prime less than lambda, and then somehow we use Pieri's rule to prove it for pi lambda. But in any case, the paper is on the archive, and Dibyendu Biswas in the middle of July.
Okay, thank you.
Yeah.
How lambda and mu appear
No.
How lambda and mu appear in finite group setting. Finite abelian group.
Yeah, so finite abelian groups are also classified by some kind of partition functions. So I think eventually the question amounts to P groups, and a finite abelian P group is given by P to the power lambda 1 plus Z mod P to the power lambda 1 plus Z mod P to the power lambda 2 plus Z mod P to the power lambda n. So indeed it has the same structure as lambda 1 greater than equal to lambda 2 greater than equal to lambda n. So the classification of finite abelian P groups is of the same nature as lambda 1 greater than equal to lambda 2 greater than equal to lambda n. I mean, yeah, so at some level, these n tuple of integers, they can come up in many contexts, but why they have anything to do with the tensor product of representations, yeah, this I have no idea.
Hi. Is there a reference for the last thing which you said, the classical group? Sorry, the finite abelian.
Finite abelian groups, I picked up,
P finite abelian group.
looking at maybe this math review of Knudsen Tau's paper. It is perhaps there in Knudsen Tau also. But I think in the years about 2000, there were a lot of articles written on this Horn's conjecture and saturation problem and things like that. I'm sure there is a lot of literature there.
Thanks.
About this A plus B equals. Yes, Horn's conjecture. Yes, indeed. Yes. Tau also has blogged about it, and but I think the path from A plus B equals C and this saturation conjecture, maybe there is no direct relationship. I think it's kind of related, but it's not that one follows from the other. I mean, for me in the lecture, perhaps it plays no role except to say that even though we seem to know everything one can about pi lambdas, to try to decompose product of these two is a difficult problem. Yeah.
Any other question or comment?
What you keep calling Young tableau is probably called Young diagram. When you fill numbers in the boxes.
Okay. So no, in many ways I am quite confused about the terminology, and Sorry.
Young diagram or Pierre's diagram?
So the Young diagram is just this shape,
Just the boxes, yeah.
and Young Pablo is
When you fill numbers
in a certain way, increasing.
column straight, yeah.
No, young Pablo is numbers filled. I mean, each entry appears only once, and the standard young tableau is when you fill the rows and columns in strictly increasing way.
Yeah, but there are various notions of standardness. Sometimes the representation theory of symmetric group, you would want every number from 1 to n occur exactly once. But yet you may allow column shift strictly increasing along columns, but weakly increasing along rows.
Yeah, semi-standard.
Semi-standard, right?
Yeah. All right. Yeah.
Okay, so if there are no more questions or comments, let's thank the speaker once again. And thank you all for coming, and thank you all online and all that for coming. One difference is between this and the online presence is that we will all go upstairs for tea and coffee and samosa, whatever. And maybe perhaps technology is not developed enough for us to share that across. Thank you. Yeah.